I will begin. Sorry. The word of prayer. Here we go. Heavenly Father, we thank you again for this day, for this time we have to meet together. Just pray you bless this class. Help us to just enjoy the math that you've created for us to enjoy. Help us to glorify you in what we do this day, Lord. In your name I pray. Amen. So, today, I'm going to talk to you a little bit about applications of linear equations. Then I'll talk a little bit about complex numbers. And then hopefully I'll talk a lot about quadratic equations. All right, so let me get started on the applications here. So, example 1. You have a winner of 500-mile race, all right, drove at 140.7875 miles per hour, all right. The question is, how long did it take him? How much time did it take? And the book asks, look, I can't speak today. The book asks us to give the answer to it within 1,000th of an hour. All right. So what's the finally? What is the rule here? What's the formula that relates velocity, speed, and time? Excuse me, velocity, speed. Let's see, velocity, distance, and time. I'll get it eventually here. How about this? The velocity, right, is equal to the distance over the time, right? But we could also write that the distance is equal to the velocity times time. That's also true, right? But that's not quite the formula we want here. This one, we want the time, right, is equal to what? Time is equal to the distance divided by the velocity, right? If we solve the first equation for t, that's what we get. Now we're given that the distance is 500 miles, right? And the speed, the velocity here is 140.7875. And what's miles per hour? That means miles over hours, right? So the way the units work here, the miles and the miles cancel, right? And you're just left with hours. So we get 500 over 140.7875 hours. And I don't know about you, but I need a calculator for that, right? What we got here? 500 divided by 140.7875. I get approximately 3.551451 blah 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 hours. So if we're supposed to round to the nearest thousandth, what's the answer? .551 is correct. And of course we mean 3.551 hours, right? So there's example number 1. Example 2 is as follows. Suppose that you invest $970 at 11% yearly interest rate, okay, for 1 year. How much interest is earned. All right, so this is a simple interest problem. So how do we calculate interest? Interest is what? Principal times rate times time. Remember? I equals PRT. That's just sad that I can't make that. Just sad. So I, interest, is equal to the principal times the rate times the time. In this case, the principal is $970. The rate is 11%. Should I put 11 there? Yeah, I wish I could put 11 there. But yeah, 0.11. And then time, 1 year. So the time is more exciting if we ask this question for like a half a year, right? For a half a year, you'd put 0.5, right? For the time. Anyway, so what we get. Get my handy dandy calculator out, 970 times 0.11. It gives me a fraction I don't care about, 106.7. So $106.70 would be the answer here. Right. Yep.
So that's price times rate times time?
Yeah, principal times rate times time. Yeah, principal. That's the amount invested. Amount initially invested. Now the same works, you know, for like if you could, nobody gives you a credit card with simple interest, but if you had a credit card with simple interest, right? If you spent $970, you would owe the credit card company $970 plus $106.70 after a year. Of course, they use continuously compounding interest, and they have a bunch of other rules and stuff, so I'm not trying to get into all that here. This is not the class. Example 3. Example 3. Suppose you got a rectangle, all right? It's got a width of 44 centimeters and a perimeter of 180 centimeters. What's its length? Draw a picture here. So we got the width is given to be 44 centimeters. The length, we don't know. And we're given the perimeter equals to, let's say, 180 centimeters. So then the question is, what's the length? Okay. So what is the perimeter? It's the length of the outside, right? So you got your W here, you got another W up here, you got another L over here, right? So if you think about the perimeter, it's what? It's twice the length, right? Plus twice the width. So if we want to know what the length is, solve for L, right? L equals to what? L equals to 180 centimeters minus twice the width, right? What was the width? 44, right? So minus 44, 2 times 44, all divided by 2. Now you might need to write a little bit more out for your own work, and that's fine. But we should all agree that we get this for L. Now plug the numbers in. What do you got? 180 minus 88. That's 92. 92 divided by 4. 46. So we get 46 centimeters for the length. There you go. Any questions? All right. So these are pretty, they should not be, I think in homework 2, your first 4 questions are kind of like these ones. They shouldn't, hopefully they're not too stressful for you, right? Okay? Just a reminder, we can do applications of linear equations. Now, that's section 1.2. Section 1.3 is on complex numbers, all right? And I won't cover everything about complex numbers, but I want to talk at least a little bit about complex numbers. What are complex numbers? You got it? Thanks. So a complex number, here's the set of all complex numbers. We use this funny looking C. It's equal to a plus ib such that a and b are real numbers and I is the square root of minus 1. So let's see here, some examples, yeah? So this means what? This means that I squared is equal to what? Yeah, negative 1. Right. So some fun examples with that, just before we do anything else. What if you had I to the 4th power, what would that be? 1, and the reason you're getting that is you're like, well, that's I squared times I squared, right? Which is minus 1 times minus 1, which is 1. Yeah, so I to the 4th power is 1. How about, you give me any power you like, I to whatever. You pick the number. Too easy. Make it bigger.
78.
I to the 78. I like it. I to the 78. Let's see. What 78 is close to 76. 76, I want to say, is 19 times 4, isn't it? So this is I to the 76 times I squared, right? I to the 76 is I to the 4th raised to the 19th power. 4 times 19 is 76. Now you could do this problem lots of different ways, but my point to you is that's I to the 4th, which is 1, right? I to the 4th power is 1. We just learned that in example 4. So we can just get rid of copies of 4th powers of I. They just go away, they're 1. And all we're left with here is the I squared, which is what? Which is negative 1. I don't know why I put these parentheses in. Sometimes I just like to put parentheses in for no particular reason. Minus 1 is the answer here. Okay, so powers of I are kind of funny. Another thing I always mention to students, because this kind of, to me it's surprising. I don't know if this even matters for this class except for this particular discussion, but here it is. I times I is equal to minus 1, right? Which means that 1, well, it means that I times minus I times I is equal to 1, right? So what happens if you take that equation and you divide both sides by I? We get that minus I is equal to 1 over I. Which is kind of weird, right? You don't usually think about flipping a fraction and going from positive to negative, do you? But the imaginary number works like that. So it does have some peculiar properties that are, not familiar. Chief among these being that the square of the number I is negative. Is the square of a real number negative? No matter what real number you think of, right? 5, 3, minus 6. Square these. The minus times minus becomes plus, right? There's something really, really weird and different about having this imaginary unit I. Now, a little bit more language here. So if you had, 17i, this complex number is called pure imaginary. This is a pure imaginary number. If you had, 2 plus 3i, this would be a complex number, right? So pure imaginary means that it's just the part with I, there's no real part. So here, this 2 plus 3i, real part 2, imaginary part, is 3. Okay, so one more, well, actually a couple more things, then we'll be done with this here. Example 8. How would you multiply complex numbers? Like suppose I have 2 plus 3i times, 7 minus 6i. How would you multiply these? Foil, right? So basically just like usual, right? So we do like 2 times 7 minus 6i plus 3i times 7 minus 6i. So I'm using the distributive property once, and then I use it a second time, which is just a fancy way of saying FOIL. You multiply them out, you keep the first the outer, the end the last. So 2 times 7 is 14, 2 times minus 6 is minus 12. We've got 3 times 7 is 21. And then 3 times minus 6 is minus 18i squared. So how about that last minus 18i squared? What is that really? So this piece right here, right, is really what? Minus 18 times minus 1. So that's really a plus 18, isn't it? It's really a plus 18. Yeah, so we're not done. We need to group like terms, right? Like put it all together. So 14 plus 18 is what? 32? So our answer here is 32. 21 minus 12 is 9, right? So 32 plus 9i. And there you go. There's so much more to say about this. Like multiplying complex numbers is actually very interesting. If we have more time and you have like take a later course, if you're, choose to add the math major, for example, you could take a course in complex analysis later. And there we might talk about like the geometric structure of complex numbers. This is actually very interesting. If you study this more deeply, the length of this number and the length of this number, right? It turns out that when you multiply two complex numbers together, the length of their product, the product of their lengths is the length of the product. So the length of this complex number is actually the length of this one times the length of this one. And also, if you study like the standard angle of the complex number, you can actually show that the standard angle of this plus the standard angle of that is the standard angle of this. So there's like a natural connection between complex numbers and rotations and dilations in the plane. But we don't need that in here, so I just say it in words. I don't write it on the board, okay? My point to you is if you want to study complex numbers further, there's so much more to learn here. And I think the terminology imaginary is really unfortunate because they are very much real in the sense of they exist and they're useful to describe the physical world. For example, electrical engineers use a complex number to model what's called impedance. So like a resistor, resistance in an AC circuit involves inductance and capacitance and just plain old resistance, and you need a complex number to describe that, how a circuit responds to a voltage source which is oscillating, right? Like the current you get out of the wall in here, for example. Okay, then finally, example 9, let's talk about how would we simplify like the square root of minus 144. So what we do here, you got square root of minus 1 times the square root of 144. What is the square root of 144? 12. And square root of minus 1, we denote that by I. All right, so this is really just I times 12, or if you like, 12i. So anytime we have the square root of a negative number, we can trade it for the square root of a real number times I. Here's another. If I have like the square root of minus 17, I can trade that for square root of minus 1 times the square root of 17. And lo and behold, we get I root 17. This is actually the main bit of arithmetic you need to learn to apply to the later part of this chapter on the quadratic formula and all that, okay? So if you understand example 9 and example 10, you got most of what you need about complex numbers. All right. I can talk about complex numbers for weeks, but let me not do that, as it would not be welcomed in here. Yeah? Any questions? Okay. With that, let us discuss the quadratic equation. So what I'm going to describe to you in the time that follows here are a few different strategies for solving quadratic equations. We're going to derive the quadratic formula using a technique called completing the square. You do need to learn how to complete the square in here. That is a required part of this course. So please do try to understand it. Now, it's okay if you don't understand what I'm about to do. What I'm about to do is a proof. It's one of about, it may be, in fact, honestly, it may be the only proof I do in this course. but I do feel obligated to do this one for you. I think it's important to see, all right? So the quadratic equation, what is it? It is ax squared plus bx plus c equals to 0. Here, a, b, and c are assumed to be real numbers, and a is not equal to 0. All right? So we're trying to solve this equation, okay? Now, if we could factor it, it would be lovely. We'd be done, right? So just let me just forge ahead here. So I'm going to start by dividing by a. So divide by a, what's that give me? I get x squared plus b over a times x plus c over a is equal to 0. All right. Now I'm going to do something rather sneaky. I am going to rewrite this as x plus b over 2a quantity squared. All right? And then I'm going to subtract b squared over 4a squared. So what I've just done right there is I've traded these two terms right here, all right, for these terms right here. If you FOIL this out, x squared plus b over 2a squared, you get back x squared plus ba over ax, because you get a half plus a half is 1, and you get an extra term, right? You get plus b squared over 2a, b over 2a quantity squared, which, to be fair, I have to subtract it here, all right? And then there's still the c over a there, so I still have to plus c over a. My strategy here is to try to factor the equation, because I know if I can factor the equation, then I know how to solve. All right? Like, if we can factor the equation, then we know that if you have the product of two numbers equal to 0, either one or the other of them has to be 0. So we're trying to factor this. Now here's the kind of sneaky step. I'm going to rewrite this as a single fraction. All right, so x plus b over 2a quantity squared minus, and watch this. So this is b squared minus 4ac divided by 4a squared. So I just made a common denominator of these two terms. And now I'm going to make a more sneaky step. I am going to, remember we talked about we can turn any number into a square? Like, what is 6 as a square? 6 is a square of what? What do? We just put a 6 in here, right? 6 is the square root of 6 squared. I just use that same trick here. So I say, well, this is really the square root of this squared. Right? Now I have this is equal to 0. And now what I can do is just do the difference of squares formula. I'll write over here. Let me write up here so everybody can see it. So I have x plus b over 2a minus the square root of b squared minus 4ac over 4a squared times x plus b over 2a plus the square root of b squared minus 4ac over 4a squared, right? And that's equal to what? That's equal to 0. Okay, so what does that mean? We have the product of this times that is 0. That means either this is 0 or that is 0, right? How can this be 0? This would be 0 if x is equal to minus b over 2a plus the square root of b squared minus 4ac over 4a squared. 0, right? And what would the difference for the other one be? Instead of having the plus here, we get a minus there. So, tell you what, let me back up just a second here, rewrite this. So what I'm saying is x plus b over 2a minus the square root of b squared minus 4ac over 4a squared is equal to 0. That would be this first term if that was 0, right? But if I solve for x, what do I get? Minus b over 2a plus the square root of b squared minus 4ac over 4a squared. But we can simplify that. What's the square root of 4a squared? I mean, so this is just from the 1, right? If we did the same thing on the other, what would happen? If I put this equal to 0, right, I go through the same algebra, but instead of having a minus here, I would have had a plus, right? Which would have put a minus down here. So anyway, long story short, we have the following. X is equal to minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. Which you might recognize, right? This is the what? The quadratic formula. So this is, you know, a stone cold formula to solve the quadratic equation in all different circumstances. Now, I rarely advocate using the quadratic formula. It's actually usually the wrong way to solve a quadratic equation. Almost always, either factoring or completing the square is a much better path. You're much more likely to get it right if you use one of those. I'll show you what I mean as we go on here. So like b squared minus 4ac is less than 0. It's complex, right? On the other hand, if b squared minus 4ac is greater than or equal to 0, you have a real complex solutions, real solution. See how the formula works? If we have the square root, if the thing going into the square root's negative, it's a complex solution. If we have the thing going into the square root is positive, it's or 0, it's a real solution. Last week we talked about prime polynomials, right? So if the solutions are complex, that corresponds to the polynomial being a prime polynomial. A prime polynomial is one where you can only factor it if you're allowed to use like complex numbers, all right? So listen, I did this proof with the letters A, B, and C in it because I wanted to make you uncomfortable and scare you and make you think about leaving the class. No, I did it because I want to give you a general derivation. But let me spend the rest of our time on examples where we actually have specific numbers on A, B, and C. But keep in mind, the pattern that we followed here, we can replicate for numerical examples. And this proof actually is a guide for how to do calculations in a particular way. So just to be clear, because I think I said a lot of different things, right? When I talk about completing the square, it's just this step right here. That is it. This is completing the square. The rest of it was something else. But this step is the completing the square step. When I talk about completing the square, if I ask you to use completing the square to solve a problem, I mean a step exactly like that one. Let me show you on an example here. Oh no, I've lost my example number. What number am I on? I just erased it.
11.
11? Is this still, am I on 12 or this is 11? 11? Okay, I'll go with it. How about this? So we've got x squared minus 6x minus, oh, I don't know, 7. Oh, 7's too easy. Let's do minus 2. All right. So this does not factor, okay? Not nicely anyway. Hey, if it factors nicely, we have an easier way to solve this. We don't need all this mumbo jumbo, and we don't need completing the square. If we can factor it, we can solve it really, really simply. I'll show you that next, okay? You're like, you're burying the lead. You should have done that one first. Yeah, you're probably right. Okay, so how do we complete the square? we take half of the coefficient of x. What's half of this? So the coefficient of x here is minus 6. So we do minus 3. So we do x minus 3. We square that. All right? Now you have to think about this. If you were to multiply this out, what do you get? You get x squared minus 6x, but you also get plus 9. There wasn't a plus 9 here to start with, so to be fair, we must subtract 9. At this stage in the game, I would emphasize that this is equal to these two terms. I'm just replacing these two terms with this squared term. That's completing the square. Now, of course, the minus 2, I still have to, it's still there, like that. All right? Now, what do we have? We have x minus 3, quantity squared, right? Minus 11, right? But I say we think of 11 as the square root of 11 squared. The reason, now I can think of it as difference of squares. Right? Like I told you guys, day one, a squared minus b squared is a minus b times a plus b. We're going to use it over and over and over. Here it again. So we do x minus 3 plus the square root of 11. X minus 3 minus the square root of 11. I might ask you to factor a polynomial using completing the square. That's what I just did here. All right, let me just put that in words. This is what I would say. We factored x squared minus 6x minus 2 via completing the square. All right. Up till now, is this an equation? Not really. Right? This was an expression. We manipulated it. How about the equation? If we look at the equation, x squared minus 6x minus 2, which is, by the way, this, right? If we put that equal to 0, right? That's a quadratic equation. What are its solutions? So either this is 0, right? Or this is 0. For this to be 0, we have x is equal to 3 minus the square root of 11. For this to be 0, we have x is equal to 3 plus the square root of 11. I don't know about you, but writing those two answers separately does not give me joy. I'd much rather just say, well, the answer is what? X is equal to 3 plus or minus the square root of 11. Now, could you have solved this problem using the quadratic formula? Yeah, of course, right? But most of you are really not that good at using a calculator. And if you try to actually plug this stuff into a calculator, bad things tend to happen. And I have a really hard time giving partial credit for miscalculation like that, you know? On the other hand, if you try to complete the square and something goes like a little bit amiss, you know, mid-calculation, I've got something to work with for partial credit, you know? And also, if I ask you to use completing the square to solve the problem and you don't use completing the square to solve the problem, then I am sort of obligated to take something off. So, any questions? So, the easier example I was advertising. How about this? What if we're solving x squared plus 3x plus 2 equal to 0? Do we need to use completing the square? Do we need to use the quadratic formula? I don't think so, right? This, we just factor this thing, right? You got yourself x plus 1 times x plus 2 equal to 0, right? And once you factor it, you can read the answers right off of that. This shows me that x is equal to what or what? X is equal to minus 1, or x is equal to minus 2. Them's your answers. No need for quadratic formula, no need for completing the square, just plain old factoring. Why didn't we just factor example 11? Because the square root of 11 is kind of hard to pull out of the thin air, isn't it? Yeah, I think. So the one way we can use completing the square to solve it is by factoring, like I did in example 11, right? The other way we could use completing the square to solve it is, sometimes it's called, what's your homework call it? Just a second, try to use the same language. Your book sometimes calls it the square root property. All right, so I'll show you what I mean by that. So here's example 11 revisited. So I do x squared minus 6x minus 2 equals to 0, right? So I'm going to solve that again, but a slightly different way. Here's how I'm going to do it. I complete the square just like I did before. X minus 3 squared minus 9 minus 2. All right? But then what I'm going to do, instead of trying to factor it, I'm going to isolate the square. Isolate the square. So isolate the square, x minus 3 squared equals to 11. Right? And then we can use the square root property that says if you have something squared equals to another thing, the answer is the thing being squared, it's plus or minus. Let me just write it down. So when I take the square root property, I get x minus 3 is equal to plus or minus the square root of 11. So if we take the square root of both sides of an equation like that, we have to allow for plus or minus because of the way the square works. You're like, why is that true? Well, I would refer you to example 11 where we derived it. So I guess this is technically example 13. And then the answer is, right?
So we need to know how to factor it and how to isolate it?
Yeah, when I factored it, I used the difference of squares idea. I didn't have to use the square root property, right? I mean, which is better, this or that? I mean, I don't know. Depends. Example 14. Maybe we're facing something like x squared plus 4x plus 7. All right? And this time I'll let you guys choose whether we want to use the factoring idea or the square root property. Okay? So complete the square, what do I got? I've got x plus 2 squared minus what? What should I subtract here to be fair? I need to subtract 4. So, just to be clear here, x plus 2 squared is what? It's x squared plus 4x plus 4, right? So x plus 2 squared minus 4 is equal to x squared plus 4x. This is the internal logic of writing this is equal to that. All I do is I take half of the coefficient of the x, I group it with x, I square it, and I have to subtract the square of whatever that half thing was. So in this case, the half thing was 2. 2 squared is 4, so I subtracted the 4. In this one, I had 6, I got 3. So I had to subtract the square of that, which is why I subtracted the 9 here. I'm going to do more of these, don't worry. Okay, so you guys, your choice. Do you want me to, oh, what did I forget? Don't forget, plus 7. So do you guys want to factor or isolate? So I got this plus 3 equals to 0. How do you guys want to proceed? Factoring or square root property? I heard square root property. I'll go that path. So square root property, I would do x plus 2 quantity squared equals to minus 3. Oh, well that's a little different, isn't it? Now we use square root property. Square root property says this is x plus 2 equals to plus or minus the square root of minus 3. But we learned that when we have a minus in the square root, we can pull it out and write I, the imaginary unit, right? So this is really plus or minus I root 3. And so the answer here is thus x equals to, move the minus 2 to the other side, minus 2 plus or minus I root 3. Yep.
Where did the negative 3 come from?
Because I moved plus 3 to the other side and made it minus. Now, example 14 looks a little bit different. If we try the factoring root is a little bit challenging here, but I should show it to you. How would you have factored? Can you guys, could you see it? How would we factor this? How would you how would you look at, so it's a tricky thing. But what you do is you rewrite 3 as minus I times the square root of 3 squared. You're like, what are you talking about? Well, check this out. Minus I square root of 3 squared. What is that? This is minus I squared, the square root of 3 squared. Minus I squared is what? It is minus a minus 1. Square root of 3 squared is 3. So you see that is just a really, really sneaky way of writing 3. But if you make that step, then you got difference of squares, and then you can factor it like we did before. See, this is just x plus 2 plus I root 3, x plus 2 minus I root 3. And then if you set this thing equal to 0, you get right back up to the solutions I had circled above. I do think that the square root property way of doing it is kind of easier for you guys to work through, right? It doesn't require that somewhat creative leap of writing the real number as a square of I and a root. You know, I get stuck on that some days, but whatever. Hey, the bigger story is this. Think about this. If you're dealing with a quadratic equation, right, and you complete the square, there are really two things that can happen. After you complete the square, the number you get is positive, right? That's one thing that could happen. If that happens, that means, I think I told you guys this last week, that means that the polynomial is prime. I called this the algorithm last week. Now I'm giving it a name. So this means that the polynomial is prime, right? It means that the corresponding solutions to the equation are in fact complex. In contrast, if you complete the square like here, say like here, right? And we get a number which is negative after the arithmetic is done, that means that the solution is real. That means the polynomial is not prime. It can be factored over the reals like this. What happens if you complete this? There's one other thing that can happen. How about this? What happens if we complete the square on x squared plus 6x plus 9? So we take x plus what? What's half of 6? 3. So we do x plus 3 squared, right? And then I have to do what? I have to subtract the square of 3, which is 9. But I already had from before plus 9. Well, that's embarrassing. So this is just x plus 3 squared. So if you happen to have the same factor repeated, when you complete the square, something kind of cool happens. The constant term and the thing you have to adjust the square with, they cancel out, and you're just left with x plus something squared. What's the solution in this case to the equation? If I put this equals to 0, that tells me x equals to minus 3, right? So in this case, there's just one solution, or sometimes we like to think about it as the solution minus 3 repeated. Because if we think about the solution as minus 3 repeated, then there's always two solutions to the quadratic equation, right? They're always given by the quadratic formula, right? But they could be what? They could be real and distinct. They could be real and repeated, or they could be complex. So, listen, we'll do more of these next time. This is the theory I wanted to share with you today. I'm in a little bit more of a hurry than I had intended for this week because I have to go to a closing for my house in Alabama on Friday. And I wanted to make sure I did some of the homeworks or examples in class, like the homework that's due Saturday, with you. So there will be a video in place of class on Friday. Because Thursday, I have to finish the material in this, course in the Thursday section. So I'll use the Thursday morning video in place of class for you guys Friday, which means you don't have to be here, unless this would be a good use of your time. Come here together and work with each other on the homework. That would be totally fine. I welcome you to work on the homework in groups. Like, that is totally acceptable, right? Make sure you find some people that are smarter than you, ideally. You know what I mean? Like, I had a good study group when I was in college. I had a couple of guys that were like smarter than me. That helps. Don't study with people. I mean, somebody should study with the people who are lost. But if all of the lost study together, it's not good. Anyway, thanks guys.
Thank you.
Professor, I had a
Yeah.
question.